resource has a positive probability of creating a defect, this has to be captured in the process flow diagram. In this session we will see how this can either take the form of scrapping the flow unit, which means we just drop it from the flow, or reworking the flow unit, which means repeating some of the operations that has happened before the defect. Either way, defects show up in the process flow diagram and have the potential to make a resource a bottleneck that, without these rework loops, would not be a bottleneck. Moreover, in addition to just changing the flow of the flow unit through the process flow diagram, defects also increase the variability in the process. Think about it. A defect probability of 10% at a resource doesn't mean that exactly every 10th unit is defective, but it's a probabilistic statement that leads to variability in the flow. And we already know that variability in flow is a big enemy in a lean operation. How do we deal with variability in flow? We're going to repeat our old tension between buffer or suffer, and we'll once again notice that there's no easy answer to this tension. Let's ignore the effects of variability for a moment and turn our attention to the following process. It's a three-step process with processing times being 5 minutes at the first resource, 4 minutes at the second, and 6 minutes at the third. Where is the bottleneck? Assuming though that there is a defect probability of 50% at the second resource. With a 50% probability, the flow unit following the work at step 2 has to be scrapped. Well, in the past we have done a rather naive analysis. We have looked at the capacity of the resources as simply 1 over 5 units per minute, 1 over 4 units per minute, and 1 over 6. If we multiply this with 60 minutes in an hour, we get capacity of 12 units per hour, 15 units per hour, and 10 units per hour. So would we really say that this step is a bottleneck? We have not considered the fact of the scrap rate. We have not considered that the units that go through step 2, only half of them will actually make it to step 3. How do we factor that into the analysis? I want you to rethink about how we tackled process flow diagrams where we had multiple types of flow units. In this case, we often look backwards and ask ourselves, what is the demand for each of the resource that needs to be served? Now assume that we have a demand of D flow units. How many units do we have to be serving at station number 3? We have to be serving D units. Everyone that needs to get served, 1 to 1, has to go through station number 3. How does it look for station number 2? Well, I have to serve 2 times D in order to get D units of output for station 3. Similarly, also at station 1, I have to produce 2D because the half of the units will be scrapped at station 2. If I now look at the demand relative to capacity, which we back then referred to as the implied utilization, I actually can find the bottleneck. 2D divided by 12, 2D divided by 15, 1D divided by 10. So the implied utilization is at the maximum at the first step over here. So we would call this step the bottleneck. And you see how the scrap rate actually is impacting where we have the bottleneck in our process. Instead of scrapping a flow unit, I can also rework it. Rework means I'm going to repeat one or several operations, and after the rework is done, the flow unit that was previously defective becomes a good flow unit. Consider the following example here. I have 3 process steps. The first process step has a processing time of 5 minutes and never does a defect. The second process step has a 4-minute processing time and with a 30% probability makes a defect. However, I'm going to catch that defect right at the completion of the step 2, and if I'm going to repeat the operation, I'm going to spend another 4 minutes, I'm going to fix the flow unit. Let's assume for now that rework also always works and fixes the unit in the first pass of the rework. And then finally I have a third step here in the process with a processing time of 2 minutes. Where is the bottleneck? Well, a very naive analysis would suggest that we just take the processing times, do 1 over the processing time to get the capacity levels, so that means 1 over 5 units per minute, 1 over 4, and 1 over 2. However, rather obviously, this analysis misses the effect of rework. Rework can make an activity that previously has been a non-bottleneck step a bottleneck, just because it sucks up extra capacity for the rework loop. So a better analysis goes something like that. Instead of saying that my processing times are 5 minutes, 4 minutes, and 2 minutes, I have to acknowledge that for the second step, with a 70% probability, it will take me indeed 4 minutes. That means everything goes well. However, with a 30% probability, it's going to take me 4 plus 4 minutes. So the expected processing time is simply 0.7 times 4 plus 0.3 times 8, which is equals to 5.2 minutes. No impact on the processing times at the first and the last steps, so 5 and 2 minutes. And I see here that the true capacity the true capacities are 1 over 5, 1 over 5.2, and 1 over 2, which reveals that really the second step is the bottleneck. An alternative calculation to get to the same idea is to use the calculations of implied utilization, which we had in the example of processes with multiple flow units. Just call the flow rate demand. Let's just assume that we're processing here at a certain unknown rate and we're pleasing a certain demand rate. Let's call this demand rate D. If we start with D, we realize that the demand rate for the first step is simply D. For the last step, it's going to be D. However, for the second step here, the demand rate is really 1.3 D. That is simply revealing that for 30% of the flow unit, I'm going to add another round of processing at the second step, and so the flow has to be 1.3 D. If you then recall our definition of implied utilization as a ratio of demand to capacity, you're going to get D divided by the capacity of 1 over 5, which is 5D, then 1.3D divided by the capacity of 1 over 4, and finally D divided by 1 over 2, which is 2D. So you notice here that this is 5.2D, which is the highest implied utilization, making the second step indeed the bottleneck. Now let's turn to the effect of defects creating variability in a process. Consider the following example of a two-step process. Both steps have a processing time of 5 minutes. Both steps also have a probability of 50% of creating a defect. In that case, their processing time goes up to 10 minutes because they require an extra 5 minutes of rework. What's the flow rate going to be in this process? Well, let's think through all the scenarios that can happen. In the best case, both of them create a good flow unit. Let's take G here for a good flow unit, and that happens with a probability of 1 over 4, and in this case we're going to get a flow of 1 unit every 5 minutes. However, it's also possible that the first step messes up and the second one does the flow unit correctly. That has also a probability of 1 over 4. Now what happens? In this case, the first resource will take 10 minutes to complete the work. However, the second resource is done after 5 minutes and is then out of work. We say that this process is starved at resource 2. Resource 2 is starved of work, and the flow rate goes down to 1/10. Now, the opposite can happen, of course, as well. The second step messes up. The first one operates correctly. Again, that happens with a probability of 1/4. And in this case, you notice that the first step doesn't have any place to put the flow unit, right? Because these guys are still now working on the flow unit. And so we say in this case, the first resource is blocked. And then finally, of course, if both of them mess up, which was also happening with a probability of 1/4, I'm also going to get the process completed every 10 minutes. So you notice that on average, the flow rate is actually dramatically slower than 1 unit every 5 minutes. That is because of the variability. If we want to avoid blocking and starving, we can put a buffer between the first step and the second step. This gets us back to the idea of buffer or suffer. The bigger the buffer, the lower the likelihood that the first step gets blocked and the second step gets starved. So inventory protects us from variability and thus helps us to obtain a good flow rate. Consider the following metaphor from the lean literature. Think about inventory as water in a river. We're operating a canal or a boat on a canal, and in the river, unfortunately, there are a bunch of rocks. These rocks correspond to all the hiccups that can happen in a process, such as defects, setup times, and other complications. Now, on the one hand, we as the operators of this boat, we prefer not to bump into these rocks. And so we have an incentive to put a lot of water in this river so that we get high above the rocks. The problem, however, is that now that we have so much water in the river, we'll never see these rocks. These rocks are not exposed, and they stay in the river forever. The same applies to inventory. If we put so much inventory into the system that we buffer every eventuality out of the way, we start taking the pressure of process improvement. So the Toyota production system in the lean literature argues actually the opposite. Instead of buffering systems, we should reduce the buffers so that we expose problems. We should do this gradually instead of taking all the water out of this river at once, but gradually, step by step, we reduce the water level and expose the most significant rock. Once we've identified the rock, we go after the underlying root cause, we get rid of the rock, and again start lowering the water level. So you notice that this creates a certain paradox. On the one hand, you need some inventory in the process just to lubricate the flow and to deal with the buffer or suffer paradox. But on the other hand, too much inventory in the system and people start slacking off. They have no reason anymore to work hard or to improve the process any further. To control the amount of inventory in the process, the Toyota production system has developed the concept of Kanban cards. Imagine we're selling these beautiful little black boxes to our customer, and the end customer demand is here on the right. We have an internal supplier, another department that supplies us with containers that include 9 of these black boxes. Once we have emptied one of these containers, we're going to take a card, a sticker that is attached to the container, and we'll move that card to this department that is feeding us with the black boxes. This sticker or this card is called the Kanban card. It's also known as a work authorization form. Now, our folks in the department supplying us, they have to sit there idle, waiting until we provide them with a Kanban card. Idle time looks very unproductive, but it's certainly better than producing inventory. So only when these guys are going to get our Kanban card, our work authorizations, are they able to produce the next set of 9 units. By definition, the work in process inventory is never bigger than the number of Kanban cards. This allows us to keep a cap on inventory, and this allows us to control the inventory level, just like with the boat on the river on the previous slide. In the early days of the process, when there are still defects or other problems, we issue an extra couple of cards. As the process gets better, we remove some cards from the system and we put more pressure on the process improvement. Now, you notice how this system is implementing a pull system. Rather than everybody in the process working as hard as they want and pushing the work forward, it is the demand that drives the system. Through the Kanban cards, the system pulls the work through the process as opposed to pushing it. Buffer or suffer. Defects provide a reason for us to hold inventory. Since we as the managers like a good continuous flow through the process, it is tempting to us to buffer the flow. These buffers then avoid that resources either starve or get blocked. The flow must go on, and so buffers help with the flow. The problem is, however, that buffers are not particularly lean. In fact, I would argue they're as unlean as it can get. And if you remember our discussion from the 7 sources of waste from the productivity module, inventory is really the worst of all the 7 sources of waste. One reason is they make us comfortable with slack, and they just make it more likely that the operators in the process just get used to defects as opposed to continuously trying to improve the process. We saw that Kanban is for us as managers a way to keep a cap on inventory, to control how much inventory can be in the system. And by setting the right number of Kanbans, we can adjust the inventory in the process to our current process capability. The Kanban process is based on the idea of pull. Instead of pushing work into the process, Kanban implements a pull where machines and operators only get activated if there is downstream demand from them, not because of idle time or input availability, but because of the need for output.